Turbulence modeling is the construction and use of a model to predict the effects of turbulence. A turbulent fluid flow has features on many different length scales, which all interact with each other. A common approach is to average the governing equations of the flow, in order to focus on large-scale and non-fluctuating features of the flow. However, the effects of the small scales and fluctuating parts must be modeled. Closure problem. The Navier-Stokes equations govern the velocity and pressure of a fluid flow. In a turbulent flow, each of these quantities may be decomposed into a mean part and a fluctuating part. Averaging the equations gives the Reynolds-averaged Navier-Stokes equations, which govern the mean flow. However, the nonlinearity of the Navier-Stokes equations means that the velocity fluctuations still appear in the RANS equations, in the nonlinear term from the convective acceleration. This term is known as the Reynolds stress. Its effect on the mean flow is like that of a stress term, such as from pressure or viscosity. To obtain equations containing only the mean velocity and pressure, we need to close the RANS equations by modeling the Reynolds stress term as a function of the mean flow, removing any reference to the fluctuating part of the velocity. This is the closure problem. Eddy viscosity. Joseph Boussinesq was the first to attack the closure problem, by introducing the concept of eddy viscosity. In 1887, Boussinesq proposed relating the turbulence stresses to the mean flow to close the system of equations. Here the Boussinesq hypothesis is applied to model the Reynolds stress term. Note that a new proportionality constant, the turbulence eddy viscosity, has been introduced. Models of this type are known as eddy viscosity models or EVMs, which can be written in shorthand as whereas the mean rate of strain tensor is the turbulence eddy viscosity is the turbulence kinetic energy and is the Kronecker delta. In this model, the additional turbulence stresses are given by augmenting the molecular viscosity with an eddy viscosity. This can be a simple constant eddy viscosity. Prandtl's mixing length concept. Later, Ludwig Prandtl introduced the additional concept of the mixing length, along with the idea of a boundary layer. For wall-bounded turbulent flows, the eddy viscosity must vary with distance from the wall, hence the addition of the concept of a mixing length. In the simplest wall-bounded flow model, the eddy viscosity is given by the equation, where is the partial derivative of the streamwise velocity with respect to the wall normal direction, is the mixing length. This simple model is the basis for the law of the wall, which is a surprisingly accurate model for wall-bounded, attached flow fields with small pressure gradients. More general turbulence models have evolved over time, with most modern turbulence models given by field equations similar to the Navier-Stokes equations. Smigorinsky model for the subgrid scale eddy viscosity. Among many others, Joseph Smigorinsky proposed a useful formula for the eddy viscosity in numerical models, based on the local derivatives of the velocity field and the local grid size. Spallet-Allmaras, K-epsilon and K-omega models. The Boussinesq hypothesis is employed in the Spallet-Allmaras, K-epsilon, and K-omega models and offers a relatively low-cost computation for the turbulence viscosity. The SA model uses only one additional equation to model turbulence viscosity transport, while the K models use two common models. The following is a list of commonly employed models in modern engineering applications. Spallet-Allmaras, K-epsilon, K-omega, SST, Reynolds stress equation model.